Okay, so today we want to talk about a very important topic in mathematics. It is called set theory. This is the first topic in chapter 2. But of course, talking about set theory can be quite hard because this subject is very abstract subject, and that's very fundamental to all of the other branches of mathematics, actually. And then we can call actually uh, Georg Ferdinand Ludwig Philipp Cantor. So in English literature, I knew this guy by the name of George Cantor. Okay, he was born in 1845 and he died in 1918. He was a very great German mathematician. Okay, and this is the same guy, of course. Here, this is around 1870, and this is a little bit later, of course, when he got old. I think we can call this guy the father of the set theory, even though the set theory he actually proposed turns out to have some small flaws, and other mathematicians actually resolved that flaws. But I think he is the father of set theory, and this person actually, if I remember correctly, is the first person actually treated the notion of infinity mathematics very rigorously. Okay. And then if I want to give you an idea of the importance of set theory, this is something I found on the web. This is more or less good. So if you see here, this is the trunk of mathematics. So you see here, the starting point is logic. Yeah, of course, you can call it mathematical logic, but there is no difference between logic and mathematical logic. The only thing that the difference is that in mathematics, we study it more systematically. And then immediately after logic comes set theory. Okay, so it means that anything after that you see is coming after set theory, even numbers. So the system of numbers are in principle in contemporary mathematics is coming after set theory, even though it's not historically this way. Historically, people knew about numbers long back before they knew about set theory. But that is an intuitive way of understanding. If you want to understand it in a more rigid way, in a very solid way, the contemporary mathematics put set theory first. So it means that when you are studying set theory, there is nothing there except sets. So you are not allowed to use even numbers when you are dealing in set theory in a really rigorous formal way. Okay, but of course at that level we are not going to address these kinds of questions. Every now and then I might give you some idea or flavors of how it's going to work, but in principle I want you to know that what is coming first in this trunk is actually logic, then comes set theory, and after set theory it comes other branches of mathematics. As you see, there are three main branches of mathematics called algebra, geometry, and analysis. And then there are a lot of branches, smaller branches coming out of these things, or a combination of these subjects. Okay, but I just want you to know that immediately after logic, we have set theory. So when we are dealing with sets, there is nothing in the world in the world of mathematics except sets. Okay. But of course, I told you I will not follow this, so I will talk about sets of numbers, even though strictly speaking, numbers are supposed to be constructed using the ideas of set theory. Okay, another problem with set theory is that the definition of set theory is, so set in set theory is a primitive notion. We don't define it, yes? And then this is a primitive notion, and there are some axioms that connect these primitive notions in the set theory, and everything after that can be proven, okay? This is axiomatic set theory. The set theory that we are studying here is actually, in literature, it's called baby set theory. And at least in Math 5, even that's not a baby, probably it's better to call it infant set theory or something like that, because we don't touch the notion of the abstract notions of set that much. Okay, so I will start with, at least I cannot define it, but I can describe it. So this is why I don't write definition of a set. I will write description of a set. Okay. Now you will understand why we cannot define it, because it becomes a circular definition somehow. So I would say that a collection of clearly, I put it in quotation mark, specified objects is called a set. So you see that this is not a rigorous mathematics. Yes, I am a little bit, I'm cheating a little bit here, because first of all, I don't know what is the meaning of clearly mathematics. The other thing is that you see I have started with the word of collection. Okay, so you might ask, okay, I'm telling you that set is a collection, then you might ask what a collection is. Yes, then I can say that that is a group. Or then you can ask me what a group is, and I can say that, okay, this is a set of things again. So you see that this is a little bit of circular argument. So this is what I'm saying. Set is an undefined notion. It's called the primitive notion in the set theory itself. Exactly like point and a line in geometry. If I ask you to define a point for me, there is nothing that you can point to it in the universe and say that this is the point, because point is an abstract definition in your imagination, and then by definition the dimensions of a point is 0 in all directions. And if something is dimensionless in all directions, you cannot at least see it, or you cannot just point to it, okay, this is a point. But for example, every one of us has a feeling of a point. Yes, if I say that, okay, let me show you a point, and I draw something like this, you immediately say that this is not a good representation of that abstract notion in mind that I have for a point. Everybody agrees that this is not a good picture for a point. But if I put, for example, this dot here, even though this dot is not an abstract point, because if I zoom in, you see it has some dimension. There are some dimensions for it. I can measure it. So it's not an actual point, but yeah, it actually somehow gives me the feeling of a real point, the abstract notion that I have in my head. So that's the idea. I want to describe a set for you without defining it clearly, so that when I write something, somehow you understand what I mean. This is a good description of some set. And here, I want to make clear that the objects that you are using here, they should be clearly specified. For example, let me make it clear. Let me clean this part. For example, I cannot write something like this. I cannot say the set of a few number of integers. Yes. So this sentence is not a good description of a set, because it is not clear, the objects are not clearly specified in this sentence. So you see, I am using the word set, I am using the word number, integers, you know them. But if I ask you, is this a good description of a set? You would say no, because the objects that I am referring to are not clearly specified. What do I mean by this sentence? By this sentence, if I ask you, for example, do you think that 5 belongs to this collection of objects? You cannot actually answer this question. because I am telling you that the set that I have thought about is actually a few numbers of integers, and I haven't given you any particular property, so that makes it clear that 5 is a member, is an object in this collection or collection of integers or not. So this is why I'm saying that you need to be a little bit more careful. You're not allowed to use this. So for example, so let me write this: not a good description, not a good description. Yes, let me. But for example, on the other hand, if I say the set of all prime numbers, yes, this is acceptable in mathematics, even though you might not be able to answer something belongs to this set or not immediately. For example, if I ask you, do you think that 7,741, do you think that this number belongs to this collection of numbers that I am talking about here? Immediately you cannot answer that, because if you want to answer this, you need to go and discover that if this is indeed a prime number or not. If it turns out to be indeed a prime number, then you would say, yes, this belongs to this set. I will talk about this later. This belongs to this collection of objects. Or it turns out that it is not a prime number, then you would say, no, this number is not in this collection. Okay, so you see that even though you cannot answer it at the time, but you know that the answer to this question, that if this belongs to this group or not, is either yes or no, even though right now you don't know which one is the answer. I hope that you understand there is a big difference between the nature of this sentence and the nature of the previous sentence. For the previous sentence, it is not a matter of time. If I ask you, do you think this number is in this collection, yes or no? It doesn't matter how smart you are, how much time you spend on it. There is not a definite answer that is this in this set or not. Does this belong to this group of objects or not? Because of the structure of the sentence itself. So this is the only thing that you need to have in the back of your head when you are talking about sets. When you talk about sets, you should say that I have a collection of objects, but they are clearly specified. It means that it is always possible to evaluate this sentence. Does something belong to that collection? The answer to this should be either yes or no, even though you don't know the answer right now. But the nature of the sentence or the nature of the set is in a way that you can, in principle, answer this question. Okay, so hopefully you understood what I mean. If there's any questions, please let me know. Is that understandable for everyone?
Yes.
Yes.
Okay, so now there are some punctuation rules, grammar rules that we need to learn. So how we specify sets. So there are some terminologies that we need to know. The name for these objects are either you can use a member or an element. Okay, so these are the words that you need to know when you're talking about sets. So let me write here. Each of these objects is called an element or a member of the set. Okay, sets are usually denoted by English capital letters. For example, A, B, C, and etc. Of course, you already know about these things because I have used them a lot. We write A and we put this symbol and then we put A here to denote that the object A is an element or a member of the set A, capital A. Okay, so we can sometimes say, so we can read it in this way. We can say A is an element of A. We can say A is a member of A. And if you remember, I have told you that we can say that A belongs to A. And for example, in LaTeX, if you want to use this, the symbol is this \in. So it means that A is in A. So these are the ways that you can read them. And of course, the negation of this, if you want to negate it, so you can write A does not belong to A. So this means that A is not an element of A. Yes? Another thing that is very important is that assume that you have a plastic bag, and inside your plastic bag you have some objects. And by the way, there is no limitation, there is no restrictions for what you can choose as the member. And they don't need to be even of the same kind. One of them can be a number, the other can be an object. But of course, in mathematics, usually we talk about collection of numbers, okay, or mathematical objects inside them. But that is not something that that's not an obligation, so you can just relax that. So the objects inside a set can be of any nature, okay? And then when you want to specify a set, there is a rule that you need to write. For example, if I want to write a set mathematically, I write A is equal to, I have to open a curly bracket, not a square bracket, not parentheses. You have to use a curly bracket. And then what you do, you will start putting the elements here. And then, for example, you name them, or you actually give a code for each object, whatever you want to do. It means that each one of them is representing an object. And then when it is finished, if it finishes, you actually close the curly brackets, and it is crucial to separate them with commas. So you have to respect what I have done here. So if you write a set like this, I will not accept it from you because this is not set. This is not a set. You need to write it in this way if you want to, for example, and you separate them with comma. So you have to open with a curly bracket, put the elements inside, and then when it is done, you can close the curly bracket at the end. Okay. So this is what I wanted to say. For example, here I can say that this one is, for example, I can write 1 and I separate it with the square root of 2 plus the square root of 3. Then I can put a letter here. Then I can put, for example, the number pi. Then I can write here a car and etc. For example, I can stop here. Then if I ask you how many elements you see in this set, I would say 1, 2, 3, 4, and 5 elements. So I see 5 elements here. So the number of elements in a set can be finite, as in this case, or it could be infinite. For example, I can talk about the set of real numbers. So the number of elements in the set of real numbers is actually infinitely many. Okay, but you need to respect what I said. You will start with a curly bracket, you have to close the curly bracket, and then you have to separate the different elements with a comma. Okay. So yeah, this is nothing very hard. So, but so you see that the elements are completely different. Here I have a letter, here I have famous number, here I have two numbers, and then suddenly I have a word here, car or whatever. And if I ask you how many elements are there, you would say 1, 2, 3, 4, and 5. So this set contains 5 elements. Okay, so if you remember, I told you that when you are dealing with set theory, there is nothing actually there except sets. So that's completely okay if I have a set of sets. Yes, for example, let me call this one B. I can have B equals to, I can open a curly bracket and close it. I can write A and I can write B, and then I can decide to write another set inside that. And then I can write, for example, E, for example. So this is also quite acceptable. So if I ask you what is this set, you would say that this is a set containing of 4 elements. 3 elements are just simple letters, but the third element here is actually a set itself. So this is also possible that the elements of a set could be set themselves. So that is the only thing. When you are dealing with set theory, there are no numbers. So it means that whatever is going to play the role of an element, it should be a set itself, because there is nothing else except sets. Okay, so that is also something good to know. But that's another thing to know is that, what is this statement? Do you think that this statement is true or false? I say that A belongs to B. Okay, so you immediately see that A belongs to a B, so I would say that this statement is true. But this is very important. For example, if I say, do you think that this statement is true or false? Yes, you should say that this statement is false. So this is what I want you to understand, because when you say that C belongs to B, it means that one of these elements is actually exactly C. But if I say that, what do you have in your bag? This curly brackets play the role of your plastic bag. And then when you go to see inside the bag, you have something of this type A, and then you have something else B. You have a complete object of this form inside your set, and then you have E. So you see that this is false, because none of them that I have listed here is exactly C, even though this is some relation with C, because inside it I see C, but this is false. If I want to write something, if I want to write a true statement here, I should say that curly brackets inside it C, then this belongs to B. Yes, this one is true. So this is very important to understand. So you cannot say that this one is true. So this is that clear for everyone? So I want you to differentiate between these two. You see that one statement is false, the other statement is true. Is that understandable for everyone?
Yes.
Yeah, okay. Okay, so that is also something I just want to mention here. And the best way of specifying a set is if you write it in this form. So for example, I would say a set A is equal to, I will describe the elements if possible, okay? So in principle, you should be able to describe the elements of a set. I would say the set of X such that the set, you see, A is equal to the set of elements X such that, this is read such that, and then I would write P of X. So what I mean that you need to collect all the terms that satisfies this condition, or enjoy this property regarding X. Okay, so this is a specification of a set. And then this can be whatever. Actually, the people who are doing mathematics specialization, this is called a predicate. So it means that in principle, this is the specification of a set. When you write X such that P of X, it means that you are giving a property related to X. Okay. So for example, let me just mention it here. For example, if I want to write this set in your group, for example, I can say, or in other groups, so I can say that the set of all elements X such that X belongs, for example, let us say Natur 19. It means that the set B consists of elements which belong to this Natur 19, but such that, for example, such that X is a girl. Okay, so this is a good way of describing the set. What do I mean by this set? If I want to list all the elements inside this set, I need to go to Natur 19 and see how many girls are actually in that class, and then I will write the name of those girls in that class, and then I will enclose it by curly brackets from both sides. So that is one way of actually describing the girls in that group. Okay. For example, if I can ask you this, a set C such that X belongs to the set of integers such that 1 is less than or equal to X squared is less than or equal to 4. And I ask you to list the elements of this set. What is this set describing for us? So you need to understand how to read it. You will say that C is equal a set consisting of X's coming from the set of integers, but not all of them, such that they enjoy this extra property, such that when I square them, they lie somewhere between 1 and 4. Okay, now if I ask you to describe all the elements here, so it is not that hard. So you can just do some simple calculation. You would say that because you are telling me that X squared is between 1 and 4, based on what I have learned in mathematics, I can see that this is equivalent to saying that the absolute value of X is between 2 and 1. I am taking a square root sign. But if I tell you absolute value of a number is between 1 and 2, you can conclude that either that number is between 1 and 2 itself, or, this means or the number is between -2 and -1, yes? Because if the absolute value of a number is between 1 and 2, it might happen that the number itself is between 1 and 2, or the number is between -2 and -1. Hopefully this is understandable. So this is equivalent to this statement. But now I have an extra condition. The numbers should be an integer. So it means that the numbers that are satisfying these conditions are only 1, 2, -1, and -2. Okay, so this is one way, for example, of writing this set. If I want to give you another example, for example, let me call this one D, the set of all x's such that x is equal to 2 to power m plus 3 to power n, such that, and it's not such that, sorry, and m plus n is equal to 4, and m and n belong to n. So this is also one way of describing a set. This is also a set. If I ask you to write it down to have a better feeling of what does this set describe, then you need to do some calculations, but you need to be able to read it. Let us read it again. This tells you that D is equal to a set consisting of elements, which we call them X, such that X is equal to 2 power m plus 3 to power n, where, you can read it where or and, m plus n is equal to 4 and m and n belong to n. Okay, so if I want to write this, how should I do that? I would say that, okay, you are telling me that m plus n is equal to 4. You are also telling me that m and n both are natural numbers. So there are not that many options then. The one option is, one possibility is that m is equal to 1, n is equal to 3. Or another option is that m is equal to 2 and n is equal to 2. Or the other option is m equal to 3 and n is equal to 1. Yes, these are the only possibilities if you are telling me that m plus n is 4 and you're also telling me that m and n are natural numbers. I'm assuming that natural numbers are starting from 1. Okay, so then, but be careful, I am not allowed to put these numbers in my set because my set are not consisting of m's and n's. It is consisting of x's with these property. And then when I know m and when I know n, I can calculate the x's that I can put in this set, okay? Now, what should I do? I would say that if this is going to happen, the x that I am looking for is 2 to power 1 plus 3 to power 3, which becomes 29. Yes? So x is 2 to power m plus 3 to power n. And then in this case, m is equal to 1, n is equal to 3. So I replace m with 1, I replace n with 3, and then calculate. So this 29 that I get is a value, is a possible value for x. And this set consists of x values. So this means this is one of the elements in the set D. Okay? And then I will do the same thing here. So I will go to the next one. And then I calculate x again here. So this becomes 2 power 2 plus 3 to power 2. So this becomes 13. So 13 is another number. And then finally I go here. I will have x is equal to 2 to power 3 plus 3 to power 1. So it becomes 11. And then I will put these numbers in a set and I would write 29, 13, and 11. Yes, so that is also a set here that we can write. Any questions? Okay. I don't know, for example, the other way around is also possible. For example, I can give you a set of numbers or anything here. So 1 over 2, I don't know, 2 over 3, 3 over 4, 4 over 5, 5 over 6. Yes, this is a set and I close it. I'm separating them with commas, actually, these are commas. Okay, can I write this in this mathematical way of writing without listing all the elements? The answer is easy. Here is easy. Sometimes this is not possible. We have to describe a lot of words to actually specify the elements of a set. Okay, but let me write this one. For example, I can say that my set, let me change my color so that this is an answer now. So I can say that the set A consists of elements. I can call it X. If you want, you can call it Y or any other letter. I choose X, but not any X. Which kind of X's? The X's can be written in the form of a number n divided by the next number n plus 1. If I close it here, be careful. I want to make sure that you understand. If I close it here, this is not correct because there is no guarantee that this combination will give rise only to these elements. Yes. For example, like if I don't say anything about n, first of all, how should one know about n? Is n a number or not? You might say that n is a number because it's clear from the context. I am doing division, I am doing addition, so n should be a number. Okay, but if you don't say what n is, people might say that n can be square root of 3, and then it becomes a square root of 3 plus a square root divided by a square root of 3 plus 1. This is an element which is generated by this formula for n equal to a square root of 3, but this is clearly not in my set. So when you want to describe the elements of your set, you have to be very careful that you're describing exactly those elements in the set, exactly those elements, nothing more, nothing less. Okay, the idea is good that I write x is equal to n over n plus 1. You might say that, okay, I add this term, n belongs to n. But this is also not good. If you just want to close it here, it's not complete, because might be if someone take n to be 10, which is possible because n belongs to n, 10 belongs to the natural numbers. And then if you put this in this formula, it will generate 10 over 11. 10 over 11 is not in your set. Okay, so this is not also, this is better than the previous situation, but it is still not complete. Yes. So what I do, I need to add something to guarantee that this will not generate even one single extra term that I don't need. For example, I can say that n is somewhere between 1 and, for example, 5. And then I can close it. So this is a description that I can write for this set. Yes?
I think you have to put a comma and then a 1 also.
Pardon?
I think something is missing.
What?
Because the first member can't be generated by that formula.
Yes, you are right. Yes, you are right. So I was
with
also
one
careless
comma.
myself. Okay. Yeah, because you are right. This one cannot be generated. So you see, that's a very good catch. Thank you very much. So you see why what Alex is saying is that if I choose n to n and n between 1 and 5, then I have to put 1 here. It becomes 1 over 2. It generates the second term, but I also have to generate the first term. So if I want to solve this one, I can write this as n minus 1. Okay, and then I clean the denominator, thank you very much, and write it n. Does this work or not? No, this doesn't work. So let me see. If I put n equal to 1, it gives me 0. The reason okay. So let me
I think
do
the
it.
first one has to be hard coded into.
No, we can do it in this way. So we can write n divided by n plus 1, but that is very good that you actually cared about this. Instead of this one, instead of saying that n belongs to n, because my convention is always that the n, the set of natural numbers, starts from 1. So what I do, I would write this n belongs to z. So I want to write, because you are right, this would be, yeah, you need to do it separately here. Yes, I was careless actually. Yeah, sorry. Let me get rid of the first one, because that is not exactly my point. I get rid of this one. If you want to add this one, you have to add it separately. Yeah, let me write it, because I have done it in that way. So let me finalize it. So yes, let me do everything from the beginning. So I would write this, x is equal to that for n belonging to n, and then n is between 1 and 5, and then I would say or x is equal to 1. Yes, as you said. So I didn't mean to write something like this, but that's also possible. So that's not a very bad way of writing. So I have two statements now here. Okay, so I'm telling you that the elements in this set are x, where either x is 1 or x is generated by this formula where n belongs to n and n is between 1 and 5. Thank you very much. I didn't pay attention to that. Okay, any questions now? Okay, so that is also one way of doing. And let me talk a little bit about extreme case. An extreme case. So what happens, do you think, if I want to write the same thing here? So for example, let me give a set E, and then I would say that x belongs to the set of real numbers such that x squared plus 1 is equal to 0. So what do you think will be inside this set? What are the elements of this set?
null, none. There won't
Nothing, yes? So you open the curly brackets, you are waiting to put elements inside, but there is nothing there, so you just close it. Yes? So you see, because if x is a real number, x squared is definitely non-negative, and when I add 1 to it, it definitely becomes a positive number. A positive number cannot be equal to 0. So it means that you cannot find any number in the set of real numbers satisfying this condition. So it means that you open the curly brackets and you are supposed to put the elements here, but you cannot find any elements, and then it means that you close it. This is called the empty set. So this is an extreme in the case in the set theory. And there are another symbol for that. This is this symbol, we use it. Okay, this is called the empty set. This is the Greek letter phi, but usually phi, when you want to write phi, you write it in this way, but they have tilted it a little bit, so that is phi, the letter phi. So, but this is the common way of writing the empty set. So when I say that I have an empty set, I have two symbols for that. Either I can say that this is this one, or I can open a curly brackets, put nothing inside it, and close it. These two things are the same symbols for denoting the empty set. So this is the smallest. We need to talk about what is the meaning of a small and big in sets, but you understand what I mean. If we consider the number of elements in a set, the empty set is the smallest one. But be careful, if I want to write a remark here, because I have seen students sometimes doesn't respect to these grammatical rules. If you write something like this is wrong, is not the empty set. So the empty set is a set with nothing inside it. Okay, if I ask you how many elements you see in this set, first of all, is this a set? Yes, because it contains two curly brackets and I have something inside it. If I ask you how many elements do you see in this set, what is the answer? How many elements do you see?
one.
One. Exactly one. And this is this object. Yes, so be careful. This is not the empty set. It is a set that this set is an element of. So be careful about this notion. This is why this is very important in sets. And the people who actually work with programming they are familiar with these notions, yes? So they have to be very careful. So don't consider this as an empty list. This is a list containing an object. In that object is itself the empty list. Okay, so even if I write something like this, am I allowed to call this the empty set?
No.
This is not the empty set. Not empty. If I ask you what is the element of this set, you would say this object is the element of this set itself. So please be careful about this point. Okay. Another misunderstanding sometimes I have seen is, let me write this remark. The relation of belonging to a set is not transitive. Okay, so some people take this for granted sometimes. So remark. For example, something in this way, say that, okay, if a set A belongs to another set, and this set itself belongs to another set, there is no guarantee that the first set also belongs to the third set. Okay, so let me just cross it over. This is not correct. For example, we can think in this way. We can say, I don't know, Alex belongs to Sweden. Sweden belongs to the United Nations, but this doesn't necessarily mean that Alex belongs to the United Nations. Okay, so that is a type of example, but you can also cook up some examples, very simple examples here. Can you cook up an example so that this statement is true, this statement is also true, but this statement turns out to be false? Let us make it as simple as possible, yes? I will write that A is equal to the set containing one single element that I call it little a. Then I will call this B to be a set containing, for example, B and little a as a set itself. Okay, and then let me say C is equal to E and B and A. Yes, something like this. Okay, now tell me, do you think that this statement is true? Let us evaluate that. A belongs to B, true or false? B belongs to C, true or false? A belongs to C, true or false? Okay, so let us evaluate them. How do you evaluate the first one? By this example that I have provided here for you, if I ask you, do you think that the set A belongs to the set B, what do you say?
Yes.
True.
Yeah, it is true, yes, because if you go and look inside B, what do you see inside B? Inside B, you see two elements. One of them is B, the other one is this one. But if you see, this one is exactly the set A itself. So yes, you are right, this one is true. But what about this one? B belongs to C. B belongs to C. Let me ask you one question. How many elements are there in C?
Two.
Two elements, yes, exactly. If you want to name them, one of them is E, the other one is the whole object here, which is a set itself containing an element and another set as an element. Okay, but if I tell you what is this, you would say this is B. Okay, so do you think now this is true or false? Hopefully, as you said, it is true. But do you think that this, the last one, is it true or false?
It is false.
It is false, yes? Because as I told you, if I ask you what are the elements of the C, you would say one of them is E. The other one is a little bit complicated object, but this is the only element. These are the only elements. One of them is written simply as E. The other one is written a little bit more complicated as this one. But you see that A, this curly brackets A, is neither this one nor that one. So the last statement is false. Okay, so this means that so this is called transitivity. So I would say the relation belongs to is not transitive. Yeah, you don't need to know the words, but this is the word if you want to know. Transitive. Okay. So this is something so you understand it, that's good. But then there are some diagrams usually we draw for visualizing sets, because for our brain is probably easier to work with shapes and figures than abstract notions. So then we have a kind of diagram here. They are called Venn diagrams. Okay, so what are Venn diagrams? So Venn diagrams, so for visualizing sets, you draw some circles, for example, or ellipses to denote sets. And then you use a rectangle to denote what we call the universal set. Okay, so let me talk about that one. So there are two extremes when you are dealing with set theory. One extreme is the empty set, which does not contain any elements at all. This is one extreme, the smallest one. And then there is a set which contains all possible elements that you are dealing with. Okay, so that is another extreme. That's called the universal set. So for the notion of the universal, let me give you the idea of the universal set. The universal set is that set. Let me write it in this way. Is the set that elements of other sets that we are working with are coming from. It is usually denoted by this capital U for universal. And this is the letter used in your book. So, and then, by the way, don't think that this universal set in theory, you don't need to have a very big set. Okay, that is a convention. If you are interested in some kind of objects to be elements of your set, you can define your universal set. But usually, if we are working in mathematics, usually the set of real numbers is our universal set if it is not mentioned. And sometimes we can make it bigger to contain the complex numbers as well. But usually in the set theory lessons, they usually mention the universal set. Otherwise, they are assuming that this universal set is the set of real numbers. Okay, so for example, what I'm trying to say, you can have a small universal set. For example, I can have this universal set. I can say that, assume that my universal set is the set of numbers from 1, the set of natural numbers from 1 to 10. Okay, and then in this case, I am not allowed to say A is equal to 1 and 11. This is not allowed. Why? Because this set contains an element, 11, which is not in my universal set. So if I fix my universal set to be this set, then I am not allowed to have this set. Yes? But for example, I can have other sets B. I can say 2, 7, 9, and 10. This is allowed, yes? That's also the notion of the universal set. But let us go back to the notion of Venn diagrams. When you have a Venn diagram, this is conventional, that you usually draw a big rectangle representing your universal set. Okay, and then you write a U here. And other sets that you are dealing, you draw inside the universal set by drawing some kind of circles, ellipses, or whatever you like, usually circles. For example, I can draw one circle here, and then I would say, okay, this is my set A. I can draw another set here. For example, it might have some intersection with that set. You see, this is an ellipse now, it doesn't matter. And then I can have, for example, another set here. I don't know if this works here as well. No, it turns into a rectangle, no matter. So that is also C. But usually I use circles and ellipses. But I am not allowed to cross the border. This is important. That is the meaning of the universal set. So for example, something like this is not allowed because some part of my set is coming outside of the universal set. So if this, usually you take this rectangle as the universal set, any other set should be contained in this universal set. So these kind of diagrams would be very helpful to to work with the algebra of sets. We will talk a little bit about this in our lesson. Sometimes it is hard to use algebra because the algebra is not part of your lesson. I will talk a little bit about that, but you can always visualize what happens between two sets. What is the relation between two sets by drawing some diagrams. These diagrams are called Venn diagrams, and that is, I think, an Italian mathematician. Okay, so that is also something that I wanted to talk. So we learned about the notion of universal set and the empty set of being two extremes in set theory. Okay, but let me just say something in passing that if I told you, do you remember I told you that the father of set theory is Cantor, and then he was usually using this, the set of all x's satisfying p of x, where p of x is a yeah, the terminology is predicate, but forget about it. It's a statement regarding x. Okay, he was assuming that this kind of objects, we can call them sets, whatever p of x is. Then Bertrand Russell, actually a British mathematician and philosopher, actually presented a paradox. So he said that if what Cantor is saying is right, it turns out into a logical contradiction if you don't want to restrict what you can put here. And this is a very simple, but if this is a little bit advanced topic, but this is understandable, I think. He said that if you are saying that I can write whatever I like here, so let me consider this set X such that X does not belong to X itself. So he was saying that, okay, because Cantor was assuming that whatever you like, you can put here, and then this becomes a set. Now, Russell realized by this very simple example that if you want to if you don't want to limit the possibilities for p of x that you can put here, this might give rise to serious paradoxes, contradictions in mathematics, and you know that mathematics cannot tolerate any contradictions, even the simplest one at all. Okay, so why this is a contradiction? It's not hard to see. I don't want to spend so many time on it, but let me just talk about this. Let me call this one A. Okay, in principle, A belongs to A and A does not belong to A. These are two statements. One is the negation of the other one. This tells you A belongs to A. This tells you that A does not belong to A. These two, one of them has to be true. If you are working in the normal logic, either a statement is true or its negation is true. There is no other possibility. So the example that actually Russell cooked up is this example, and he's now asking, because you are telling me that I can put whatever I like here, so I chose to put this predicate, this statement regarding x here. Then let us see what would be the contradiction. Then you are telling me that this is a set. Then there are two possibilities. Either A belongs to A or A does not belong to A. But let us see why this is a contradiction. Can you see it? What is the consequence of saying that A belongs to A? Can you see what happens if A belongs to A?
The definition becomes recursive.
No. So what I'm trying to say is that what I'm saying is this: if you consider this according to Cantor, this should be counted as a set. But now, when this is a set, we can ask this question: A belongs to A does not belong to A. There are two possibilities, either this one or that one. But then, when I say A belongs to A, what does it mean? It means that A satisfies this condition. Otherwise, it was not in A, because what I put in A are those elements or those sets that does not belong to themselves. When you say A belongs to A, it means that it cannot be in A. So the conclusion is that A does not belong in A. Yeah, is that hard? If that's hard, I can skip it, okay? So it is a contradiction, because when you say A belongs to A, I can conclude that simultaneously A does not belong to A. But this is a contradiction. On the other hand, if A does not belong to A, because it satisfies the criteria of this set, I have to admit that A belongs to A. And this is a contradiction. Not because I am doing something wrong, because this idea that whatever you put here turns this to a set is a wrong idea. So it means that if you are not careful and write whatever you like here, you might face some contradictions, some serious contradictions that you cannot get rid of that. I don't know, if you want, we can discuss a little bit about this, but that is completely beyond the scope of this lesson. Yeah, I don't want to confuse you, but if you are interested to talk about, let me just know if you understand it or not.
I think I understand
Yeah.
personally.
So can I cook up another statement like this? So for example, something like this. This statement is false. Is that correct? So is this true or false? Something like this. I don't remember exactly. When I say that if this, so this sentence is false, then I want to evaluate it. Is it true or not? If this is true, according to the sentence itself, it should be lie, it should be false. And if it is false, then it is true. Yes, something like this. I don't remember it exactly, but in mathematics, it is easier for me to think. Yes, hopefully you understand that. So if you don't understand the conclusion, but at least I want you to understand something. It is not easy to say that, as a Cantor told us that if we put here x and put whatever we want here, then this is a set. But Russell actually cooked up this example. He said that, okay, you are saying that whatever I put here is okay, so I put this one, and then this gives rise to a contradiction. So the bottom line is that I have to be very careful with what I want to put here. Otherwise, I would actually face some contradictions. Okay, so let us skip this one. I shouldn't actually talked about this at all. So you can just completely ignore this part. Okay. And this is it. Let me see what more I can say today. Okay, I will talk about two important points about sets. In sets, order is not important. Repetition of elements doesn't change the set. So this is the last thing that I want to talk today, and then we come back actually later in the next lesson on Monday. Okay, so let me start a definition here. And these are the consequences of this definition. Okay, I would say two sets A and B are said to be equal if they consist of exactly same elements. So what does it mean? It means that if X belongs to A, that X also belongs to B, and if X belongs to B, that X also belongs to A. So they are exactly containing the same element. So you see that in the definition of equality of two sets, by the way, we use the same symbol A equal to B. In the definition of the equality of two sets, the order of the elements is irrelevant. Nothing is mentioned about the order of the elements in a set. Yes. So for example, if I have this set, A equals to 1, 2, 4, and then I have a set B equals to 2, 4, 1. These two sets are exactly equal. So be careful. So the order is not important in a set at all. There is no difference by definition between this set and that set because they contain exactly the same element. Whatever is in A, it is also in B, and the other way around. Whatever is in B is also in A. So this is the A equal to B. So this is also the same thing. This is why people doesn't repeat an element in a set. So for example, if I have a set equal to 1 and 2, and if you have a set B, which is 1, 2, 2, 1, this is why these two are exactly the same again. This is why we never repeat an element more than once. So here, if I ask you what is the A and B, I would say that A and B are again equal. Okay, because whatever I see here, I also see here. In how many places? Who cares? 1 is here, it's also here. You can also refer to this one. 2 is here, this is also here. And then when you look back here, whatever you see in this one, you can also see in this one. So this is why, by convention, whenever you talk about a set, automatically we mean we are not repeating an element. If that element is in the set, I write it and unwrite it only once. I am not allowed to repeat it. Okay, to repeat it. Okay, so this is something that I want you to know as well. So the order is not important. The repetition of elements by convention is not done. So we shouldn't repeat an element with more than once. Okay, if we do, I am not creating a new set by definition. Okay, any questions? Okay, I think it would be good if I stop here. I will write on a school soft which pages on the book you need to read and which exercises you need to do. I don't know exactly, are there some exercises related to this, but there are some of them. I will refer them on a school soft and then we continue on Monday. Is there any questions?
Nope.
Okay, so let me just stop this sharing and let me also stop